So today our target is to study essentially three things: limit, continuity, and differentiability. But as it happens, our objective here is not actually of a IIT kind, that is, take 5 problems and take 20 formulas and then you know try to do some mix and match and get an answer. That's not the kind of discussion that we are going to have. Our objective here is actually to learn what are these limit, continuity, and differentiability as concepts, how do they work, what backgrounds are basically needed when they do not exist, why they do not exist, and if possible, we will try to understand, visualize it to a certain extent. And because of that, the background or the starting point of this will be quite different. Okay, so as I said, our interest primarily is not give me the answer of limit x tends to 0 some function. Our interest is when you are mechanically doing that, like sort of a robot, what you are actually doing in the background. Now, just to start with, the all of this, that is limit, continuity, differentiability, they are basically part of real analysis at large. Okay, they come as a part of mathematical analysis, and to that extent it goes like this: limit is a more bigger idea. We put some restrictions in that and we get an idea called continuity, and then we put some further restrictions and we get the idea of the concept of differentiability. So it starts from the very idea of set theory, just to give you the background so that you understand and be able to connect whatever you have studied till date. So we start with set theory. In that, we study something called a Cartesian cross. Okay, Cartesian cross. And this Cartesian cross is something that connects us to the two-dimensional or three-dimensional geometric objects that we used to draw in middle school or something. So from this Cartesian cross, we go to a concept which is called relation, which puts some restrictions. Then we go to a concept function, which put some restrictions on this. Then from function, we come to limit, which is the most important concept of in the whole of calculus, and then continuity, and then differentiability. Okay, that's how it works. So when we are starting with limit, I'm assuming the fact that you understand what a function is, not how I write a function, but what actually a function is. Okay, how some ordered pairs are, a set of ordered pairs become a function, and another set of ordered pair does not. Okay, so we start with the idea, with the definition of this. So definition of neighborhood, of a point. Okay, so that means this definition precludes the idea that there is a point. And not only that, the second important thing is the term neighborhood doesn't exist at its own. It exists with respect to a point. Okay, so this is the preliminary, or this is the prerequisite kind of. It's a prerequisite to understand what limit is. Okay, so what it is? It's very simple. Any open interval consisting a point P, okay, consisting of point P as its midpoint, as its midpoint is called a neighborhood of P. Is called a neighborhood of P. Okay. So as a definition, this is pretty straightforward, and also it is very easy. So I take P and I consider an interval around P so that this P becomes a midpoint. Okay. So if I take a distance of this much to the right side, I must take the same distance to the left side. All right. That's very important, because otherwise this P won't be midpoint. So what will change if I take this much amount of distance on the right side but a longer distance on the left side? Will this not be a neighborhood? Yes, it will be a neighborhood, but the problem is then this neighborhood will be around a point which will lie here, some Q, but not around P. So if I'm considering a neighborhood of a point P around P, then that P becomes the midpoint. Okay. So to that extent, it is pretty geometric. You have seen such diagrams, but not probably this language. We have several ways of writing it. So let us look at some notations, because these notations we'll be using them to write the definition of limit of a function around a point. Okay. So it is denoted by so we can write NP to denote one neighborhood, then N1P to denote another, then N2P to denote a third one, etc. Okay. So in this way we can write a series of neighborhood actually. But let's take a look at some other style of writing this. So for example, so NP, let's say NP is an open interval. Let's say that NP is an open interval symmetric around P, because P is the midpoint. So it will be symmetric about P. And that means what? That means or we can write hence here. So hence it can be written as a collection of X such that X lies between P minus R and P plus R for some R greater than 0. Okay, so this basically uses the idea that first appeared in your mathematics as in circle. Okay, so there is some P. So I fix a radius here, P plus R and P minus R. And by neighborhood, I mean all the X that belongs here. So it's the same thing. So this is one way of writing it. And from this one, I can derive some other way of writing also. But anyways, first of all, what is this R? So to keep up with the terminology, this R is called the radius of the neighborhood. The radius of the neighborhood. So what does this tell us? This tells us that instead of considering N1P, NP, N1P, N2P, we can actually consider a series of radii, and each radius will connect to a different interval. Okay, So that is another way of writing the same thing. All right, so this will become really important when in future you will have to study, you know, real analysis under the name real analysis. Okay, so if we want to specify, to specify, write n of p semicolon r. This semicolon stands for the fact that p and r, they are kind of they are of two different characters. So the radius appears here, and this is the point about which I am considering the neighborhood. Okay, so this is far more explicit than simply writing NP. But when we are actually not concerned about different distances or different length of radius, in that case we simply write NP, which we'll be writing in case of defining limit of a function about a point. Okay. So now if we take a look at this, so writing this, which we have written here, is equivalent to minus r less than x minus p less than r. And that essentially means I'm writing mod x minus p less than r. Okay. So in lower classes, you have, if you have studied limit earlier, then you have come upon a definition which is sometimes called epsilon delta definition, just to segregate with the other one. So you can see that structure of that definition matches with this, and this idea also kind of reimposes the fact that the first you have first come across such symbols when we were talking about circles in geometry. So anyways, so a strictly less than means we are talking about open interval, and if I make this weak inequality, then it will be a closed interval. But for the time being, we are interested more in open interval. Okay, so given this idea, let's write something about limit. Okay. Okay, so now we will go to the definition of a limit of a function. So definition of a limit, rather of limit of a function. Okay. So the name itself suggests that we need functions to work with limit. Okay. So how to write that? The symbolism limit x tends to p f of x equal to a, or we can write like this: fx tends to a as x tends to p. Why writing this is important? It is because when you first write this, somehow in some people's head, this is what gets in, that I'm writing fx equal to, this equality is connecting fx and a. That is wrong. Okay, this equality is not connecting fx and a. It is mathematics, so what is written, that is only true and nothing else is true. So this equality basically connects this a, which is a value, and this whole thing. Okay, so limit x tends to p fx. This entire thing is equal to a. Not only fx is equal to a. Why? Because fx at p, whether fx at p is equal to a or not, that is not our concern. I'm not interested in whether FP is equal to A or not. But when I'm writing it in mathematics in solving problem, I'm putting this equality. The reason is that if I introduce the concept of limit, then this fx around P and not at P, around P, it equals to A. Okay, try to understand this, because otherwise, you'll never be able to solve something other than those regular problems. Okay, so what it means? So this symbolism means that for every neighborhood, N1A, that is around this A, there is some neighborhood N2P such that, so before writing such that, what is that? Just understand that it starts with a neighborhood around A, okay, not a neighborhood around P. It starts with this. For every neighborhood of A, there is. So first job is to define this one, and then we need to find a neighborhood around P such that some condition is satisfied. That is the idea. Okay. So one thing is that, so first thing to learn is that it starts with A, that is the value. Second thing is that I'm writing for every. This is a very important term. Every means, that means this R that we talked about with respect to the neighborhood, this R can be as small as possible, but definitely not zero. Okay, so this idea in English, we write this word as infinitesimal. Okay, infinite, ESIML, infinitesimal. Infinitesimal means as small as possible. Okay, so this infinitesimal is the idea here, but positive. So that's why you always, that's why you have come across this famous structure, epsilon strictly greater than zero, however small. If you have read a mathematics book, you have seen this. Okay. So this word basically is a different way of writing this term every. That's what every stands for. Okay. Such that fx belongs to N1A whenever x belongs to N2P, and that is the most important thing, and x does not equal to P. Okay. So that means what? That means if you find that at x equal to P this is happening, that doesn't carry any point for you. Okay. We are interested in the smallest possible neighborhood, not at x equal to P. Whether it happens or it does not happen, we do not care. Okay. So then the central question that comes in our mind that this is that when that is then why, while evaluating the limit of a function, I put this P in place of x. Why do I do that if I'm not interested in x equal to P? Because that is exactly what I am doing every time when I am solving the problem, right? And yet in the definition I'm saying I'm not interested in what happens at P. So why do we do that? We do that because we are not finding actually what our problem is. Not this. Okay, we are not finding this. This is something that we are not finding. What we are finding is this. So that is why it is important to understand that this equality is connects A with fx under this limit and not otherwise. Okay, and you have seen that. Okay, so this is how we work. Anyways, so let's look at another way of defining it. Okay, where we have a other we have the alternative writing for every neighborhood. So you can write probably alternative definition, yeah, that you can write. So here you can write alternative definition of limit of a function. So the symbolism again that we have to start with: limit x tends to p, f of x equal to a means that for every epsilon greater than 0, there is a delta greater than 0, the neighborhood of P, such that so mod of fx minus a less than epsilon, so that's every neighborhood around a, whenever 0 less than mod of x minus p less than delta. Okay, so instead of writing neighborhood, we introduced two symbols and we have saved space. And also this gives us a far clearer understanding of when I'm given a problem where I have to show that the limit does not exist. Okay, not because I mean not in the way of right hand limit and left hand limit are unequal or something. If I have to say disprove something using geometry, so to say, or because the limit is I mean there is no limit, that is it is going being doing something undefined or something, or it is going to infinity, so to say. In those cases when I'm reaching a larger and larger number, in those cases basically this epsilon delta definition, as, okay, this definition comes into help. This actually makes you understand what you are actually doing. Okay, and otherwise for simpler problems you know how to solve them. Okay, so three writing styles. Why? Because sometimes expressing the given problem in different way actually helps us think, and also understanding that we are writing the same thing gives us a better understanding. So we started with the symbolism limit x tends to p fx equal to a. So what we can do is we can always use addition subtraction ideas the way we have used it. This, but when I'm writing equal to 0, I have to put them into bracket. So suddenly the limit here is working on fx minus a itself. But since a is a constant number, you can understand how that works, right? Okay. And obviously you have the use of modulus sign. So these three statements, they are the same. Okay, that is they are equivalent. Okay, so let us erase it. All right, so now here we have used the idea of a neighborhood, and we know that neighborhood has a concept of symmetry. So, but it's not the fact that there is only this kind of limit that you may have to work with. So there is something called one-sided limit also, that you know that the right-hand side and left-hand side limit, they can be defined separately. And actually finding them is important to find whether the limit exists for a function or not. So let's go to that. So one-sided, as you may call it, okay. So one-sided limits can be defined as follows. So the right hand side, limit of A at P, written as, so how do we write it? Limit x tends to P plus f of x equal to A. Means that for every neighborhood n1a, so we go in the similar way. For every neighborhood n1a, there is some neighborhood n to p such that so fx belongs to n1a whenever x belongs to n to p and right hand side, so x is greater than p. Here also note that we have not written x is greater than equal to p, so x is greater than p. So obviously if we talk about diagrams, so basically if this is a function and this is my some a, and if this is my fx, and corresponding to this a, if this is my fx, okay, or no, rather we will put it like this. So sorry, if sorry, this is, if this is fx, so if this is my p, sorry, if this is my p, so then I am on the right side, so I'm coming from the right side to p, right? Okay, and so I'm defining a neighborhood around a like this, okay, and so this is right hand side, so I'm defining a neighborhood around a, so this is my a, right, neighborhood, and that will bring us a neighborhood like this, okay. And my, what is my target? My target is whether I can find that the function is still in here, okay. So that's pretty miniature. To take a bigger diagram, what I'm saying is that this is my fx, this is, let's say, my a, and this is my p. I'm coming from this side, I'm taking an interval which will give us an interval here, okay, and I'm looking whether this f function is in between this zone or not. Okay, try to understand that the function may not exist here. I have no issue. Or the function may have some different value at specifically p. But I'm interested in what happens on the right side of p. Okay. All right. So that's what we are interested in. And then only I can say that the limit of the function around p is this a. Okay. All right. So to that extent, if this is the drawing of my function, then at this point I can easily, using the same diagram, and at this point, let's say this point is some q, I can go and define a left side limit in the opposite direction, right? Okay. Anyway, so you look at diagrams, you solve problems, you will understand, or you re-study and try to think what you are doing. But the idea is simply this. But obviously, as I said, that when I'm saying every neighborhood, I'm talking about a neighborhood which will be quite difficult to distinguish from the point A just by looking. Okay. So now we will look at three different functions, and we'll talk about the limit of those functions around some points. Okay. So the first function under discussion is this. Number one is fx equal to, we famously known as box x for all x. Now, in order to find limit, I need a point, right? So let p be any integer. Okay. So we know how this box x behaves, right? So we can write like this, that fx equal to p minus 1 when x is less than p, and the same fx is equal to p when p plus 1 is or x is, okay, we write like this. You can write like this, when x is less than p plus 1 and x is greater than p and also equal to p. Okay. So this is basically how we can define the box x for an integer p. Less than p, it is p minus 1, another integer. When it is equal to p, then obviously it is p. Okay, it's fine. And for again less than p plus 1, we have this. So here, this is what we have. Okay. So before going into limit, let's look at the diagram, because that helps. So since x is any integer actually for all x, so this is 0, 1, 2, 3, and minus 1, minus 2, minus 3, then the diagram basically goes like this. Right? Yeah. Okay. Is that correct? Okay. So when it is 1, the value of fx is 1, and as it reaches to 2, oh, sorry. Yeah, as I was thinking. Let's draw it like this. 0. Okay. Let's make it simple. Okay. So when it is 1, if x is 1, so when it is 2, it is, so let us write like this. Yeah. So when it is 1, it is 1. And when it is 2, it is 2. But as long as it is not 2, if x is 1. Right? Sorry. So it goes like this. Okay. All right. And here it goes like this. Okay. Now, in order to write, how do we write this? We write it very simple. We write that the left-hand side limit p minus of fx is p minus 1, and the right-hand side limit, that is plus, is p. And as the right-hand side limit, or we can simply in English, as these limits are not equal, the limit does not exist. Right? Yeah. Okay. Because to see geometrically that if I make a neighborhood, then I'll not be able to find that. Okay. So this is how it works. Okay. So let's go to the second one. So the second one is fx equals to 1 by x square for all x not equal to 0, and f0 is 0. So what is the graph here? The graph here is basically this, and here is a point 0. Right? So the graph goes like this and then comes down like this, but at 0 it is 0. Okay. So now if I look at this, it's easy to derive actually, but anyway, so if I look at the function, then I realize that f takes arbitrarily large values near x equals to 0. Right? So that neither it has right hand side limit, neither it has right hand side limit, nor left hand side limit. Right? It doesn't have either. So that means limit does not exist. Okay, now here we see a point where if I have to rigorously show that, all right, if I have to rigorously show that, here I need that epsilon delta definition. Here I need that epsilon delta definition. Why? Because to show this taking arbitrarily large values. Because here the proof will rely on the idea that if I take a neighborhood, okay, so if I take a neighborhood of fx equal to a, so if this 0 becomes my a, and then if I take a neighborhood, then for every neighborhood, then whenever the function is near 0, what will happen? I'll not be near the origin point, but I'll be near this, I'll be in these two extremes, right? So the function fx indeed approaches 0, that there is no problem. But when it doesn't approach here, it takes arbitrarily large values, right? So in that way, I can show that this function does not have any limit. But obviously, as I said, that this proof or the answer, it will not follow your standard RHL not equal to LHL, but basically you have to write in terms of epsilon delta. So that's how the idea of neighborhood actually works, always in the background. Okay, so let us go to a third example. Okay, so let's look at the third problem. Okay. So the third one is, so fx equals to 1 if x not equals to 0 and f0 equal to 0. Okay, so let's look at this function. So x, fx, and if this is the 1 here, and this is 0 here, then the function goes like this. It comes like this. Then at this point, it reaches 0 suddenly, and then it goes like this. So this function, it obviously has limit because the right hand side and the left hand side both equals to 1. We know that. So what it teaches us is basically the fact that we are not concerned about what happens at x equals to 0. So no concern at x equals to 0. And because of that, since the function changes its value only at x equals to 0, it doesn't bother us. So it has limit and limit x tends to 0, f of x is equal to 1. Okay. Okay. So what it teaches us again is that although f0 is equal to 0, the limit is 1, the limit is not 0. All right. So this is what tells us that the approach that you have probably learned 1,000 times, that, oh, you have to find limit, put excess value here, that doesn't really work. And this is how that doesn't really work. Okay. Because we are not concerned about the value at x. We are concerned about what the value at the neighborhood. Okay. So these three problems, they basically teaches us the underlying concepts of when limit exists, when it does not, and the most important fact that in finding limit, we are not concerned about what happens at zero, the value at zero. So here we are not getting the value of limit as what the function takes at zero. We are getting 1 because in every possible neighborhood, the function's value is 1. Okay. So this basically concludes our conceptual discussion of limit. As I said, that I think in simpler, regular, everyday problems, how to find limit of a function. Okay. But one last thing I also want to add is that this whole scenario is based on, remember, based on the fact that we are trying to find the limit at zero. Okay. So as you can understand that this zero is pretty important. It has an important role. And also obviously the values at RHL and LHL. Okay. So now we will move on to the what we call them as basic limit theorems, which essentially means that there are some theorems which are little bit advanced, or to that extent which are based on these limit theorems that we are going to write. Okay, now these limit theorems, they're intuitively very easy to understand. Okay, so take a look at how I am writing it, because that is important. So let f and, okay, this looks like f. Okay, so let f and g be functions such that limit x tends to p f of x equals to a, comma, limit x tends to p g of x is equal to b. Then we have, so before taking a look at what we have, let's make a note of the facts that the points around which I am finding limit, they are identical. Okay, although the values are obviously different because the functions are different. So limit of function around a point, that point is p in both the cases. This is important because without that, the limit theorems will not really work. Okay. Okay. So limit x tends to p. Now these are very, very simple. Okay. F of x plus minus g of x, I am combining two results basically into one, okay, is equal to a plus minus b. So this is trivial. Number two is limit x tends to p fx into gx is equal to a into b. So I have separated for quotient because for the third one we have an extra condition. Okay, and the condition will come. So limit x tends to p fx divided by gx is equal to a divided by b if b not equal to 0. So that means for the quotient, obviously, like the other ones also. So first of all, in each of these three cases, these limits, they have to exist. Okay, that is the first thing. And they have to exist about the same point. All right. So if one of these doesn't exist, then this whole result will break down. And lastly, in the third case, not only the limit of gx has to exist, but it has to be something other than 0. Okay, so when I'm writing if b not equal to 0, I'm not saying that limit does not exist. I'm saying it may exist, but it cannot be equal to 0. Okay, So these are the three basic limit theorems. I'm actually combined one into two results into one. Okay, and we'll now go to uh, a result which is based on this. I mean, which is based on the concepts of limit basically. A result which involves limit, and I think that you have actually seen that one also. Okay, so this one I'll write it as squeezing principle. I have heard that in some places it is called sandwich theorem, which I do not like the name. Okay. So what is squeezing principle? So it says that suppose that fx less than equal to gx less than equal to hx for all x not equal to p. I could have used a symbol here, but the reason I did not use is that it's a separate line, that's it. So for all x not equal to p in some neighborhood, so now we are assuming that you are quite friendly with the word neighborhood. So in some neighborhood NP, okay, suppose also, so the premise doesn't end here. Suppose also that limit x tends to p f of x is equal to limit x tends to p hx is equal to some a. Okay, a is a number basically. Then we also have limit x tends to p g of x is equal to a. Okay, so what it basically tells us is that if I know this relation to be true for all x not equal to p, and if these two are the limit of these two are same, then the middle one will also have the same limit. Okay, so as simple as that. All right, so now we will move on to the idea which comes just after limit, which is continuity. So now we will move on to continuity. Okay, now remember one thing, that when we have studied limit, we have said definition of a limit of a function, and we have stopped there. But now look at what I'm writing. What I'm writing is definition of continuity. Definition of continuity of a function at a point. At a point. And why is that? Because now I am interested in the point. In limit, I was not interested in the point. The point was given to me as a reference. It is the neighborhood around that point in which I was interested. Okay. All right. So a function f is said to be continuous at a point P if A, F is defined at P, because now I am concerned. So as happens in mathematics, as we talk in about this instability conditions, that we are first interested in the existence. So F is defined at P, and B is very simple. B is limit x tends to P, f of x equal to f of P. Okay. So the reason that generally this line is omitted when you first come face to face with the idea of continuity is that the function that you dealt with, they were defined generally at P. So it is never explicitly said that this is a requirement. And the downside of this is that you generally you forget the fact that it has to be defined. Okay, and you struggle a little more, and you then find that, because you see, to complete the problem on the right side, I do not need this. I do not need define that P, right? Because I'm not concerned when I'm finding limit. But this is on the left side. But to write something on the right side, there I need this. So this is why this comes as a prerequisite, and then I write the line. I'm defining using the idea of limit. Okay. So this is how. So what continuity does is basically, in the set of possible limit values, continuity restricts the limit value to be only f of p and nothing else. So if it becomes nothing, if it becomes f of p, it is continuous. If it becomes something else, then it has limit, but it will be discontinuous. Okay. All right. So all right. So now we'll look at two other definitions of the same thing. The why we will do that? We'll do that to just to answer a fancy, and that fancy is, what would have been the definition of continuity of a function at a point if I would have tried to write it the way I have written the definition of limit. Okay, so the first one is that, so it will go like this: a function f is continuous at P. A function f is continuous at P if for every neighborhood n1 and now I'll write n1 f of P. Okay, so the things have changed a little bit. So what has changed is now I am writing f of P. Why? Because looking at the earlier form of the definition, I know that this time that A has to be f of P. So n1 f of P for every neighborhood, n1 f of P, there is a neighborhood, and then it will go like earlier. There is a neighborhood n2p such that fx belongs to n1 f of P whenever x belongs to n2p. Okay. So this is what has changed. A has to be f of P, so I just inserted it, and my definition of limit make the way for definition of continuity. So let us look at the third way. which is the again the epsilon delta definition of continuity. So a function, sorry. So a function f is continuous at p if for every epsilon, if for every epsilon greater than 0, so let us use some symbol, there exists a delta greater than 0, this looks more rigorous, right? such that mod of fx minus f of p less than epsilon whenever mod of x minus p is less than delta. So now we understand what that epsilon delta definition stood for. So now we will, in the next, we will go back to the three problems that we covered in limit, and there was a purpose of doing it, was purposive totally. So we'll look at three different types of discontinuities, uh, and only one of them, which is called removable discontinuity, that is a type of discontinuity from which there is a new class of problem that appears. So the name of that is removable discontinuity, to tell you the fact that you can actually change something in the function, not really changing the function entirely, but you can change some value of the function at some point, value of the function at some points, and you can remove the discontinuity. So there is a class of problem which asks you, you know, the question that what value of this function, what value of this function needs to be changed to make it continuous. Okay, so there is a set of problems like that. Okay, so let us go to those three problems. So now we look on to three problems, and yeah, so the first one, so it's the same one, fx equals to box x for all x. Okay. Now for this problem, earlier we saw that the limit does not exist around an integer, but otherwise the limit exists. So that means if I have to write this function is continuous. This function is continuous at every point p, which is not an integer. There is another way of writing it. We can write in the negative sense also, that this function is discontinuous at countable infinite points, because that's what the set of integer is, countable infinite, so countable infinite points. Okay, now from this, again, this also generates a class of problems. And what is the question? The question is that if someone asks you to find flatly, comment on the continuity of this function, then you have to consider really for all x. That means you have to think actually, okay, where it is discontinuous. So when in general, when there is, the question is not giving you a point. Okay, so if it says that find the comment on the continuity of this function at an integer, then your job is pretty simple. But if it asks comment on the continuity of this function, then first you have to think, use looking at this function or probably drawing the diagram where it can be discontinuous or where it may be discontinuous. Your first job is to find those points. Okay, so you start from the negative side, and then to ensure that at all other points it is continuous, you just have to check once, and that's pretty easy. Okay, so this is a comment based, which is on the discontinuity or continuity of the function, not a single point but all the points in the domain. Okay, so that's a class of problem that may be new to you. All right, so now this introduces to us something we called as jump discontinuity. So what is jump discontinuity? Where discontinuity occurs as RHL, that is right hand limit, is different from the left hand limit. So that is called jump discontinuity. Suddenly there is a jump. So if you look at the function, you will, if you look at the diagram of the function, then you will actually see that this word basically comes from the geometric pattern and not from a very strong mathematical background. Okay. Again, you see, we have said that it does not exist. It is not continuous at integer points, but otherwise it is continuous. So we can also write a statement like this, that if p is an integer, f is continuous from the right at p, continuous from the right. Okay. Now, generally in continuity problems, you will not get questions where one-sided, it will, where you will be asked to use an idea of one-sided continuity. It will not be asked. But the reason of writing this sentence is that you can actually think in this way, and that becomes helpful sometimes when you are working with differentiability. Sometimes. Okay. But in general, this is the 2 points of learning is here. Number one is a type of problem that can be given from this idea, and the second is what is jump discontinuity. Okay. Now we'll go to the second problem, and we know that the second problem is fx equals to 1 by x square for all x not equal to 0 and f0 equal to 0. So we are interested at x equals to 0. And we know that the limit does not exist. So the function is discontinuous. The function, that abbreviation of mine, is discontinuous at x equal to 0. Now, why we are interested? Because this type of discontinuity is called infinite discontinuity. Infinite discontinuity. Okay. And it is infinite discontinuity. You know that why it is named such, because so you can just continue writing as the function takes arbitrarily large values near the point. Okay. But if you look at the diagram, you know the diagram. In the diagram, if you look at, otherwise the function is continuous. There is no problem, right? But at 0, it is discontinuous. And it is named as infinite discontinuity. In the third one, we will look at, in the third problem, basically, we will look at a different kind of discontinuity. Okay. And for that matter, we also know what the third problem of us is, and that is fx equals to 1 for all x not equal to 0, and f0 is equal to 0. Okay. Now, what is the nature of this discontinuity? Much like the earlier problem, this function is discontinuous only at x equal to 0. Or if we write the affirmative sentence, then we will write this function is continuous only at, no, sorry, continuous, not only, sorry, everywhere except at x equal to 0. So that means what? That means keeping the function what it is, and we know that the limit exists, and we know that the limit at around x equal to 0 is limit x tends to 0 fx equal to 1. All we need to do is we have to redefine fx only at x equals to 0. So otherwise we can keep the function as it is, but we have to only redefine fx only at 0, and that will solve our problem, and that will make it continuous. Redefine fx only at x equals to 0 and make fx as we write it everywhere, continuous. So this is something that we call as removable discontinuity. Now note the idea very clearly. See, if we change the function itself, then every function can be made continuous. There is no doubt of that. Then why this is the kind of discontinuity we are calling removable? Because here, to remove the discontinuity, to make the function continuous, I don't have to change the function for most of its domain. Or for that matter, we don't have to really change the function in that sense. We just have to change the value at only one point, at a very single point. Okay. So that means removable discontinuity can allow us to change the value of a function at some very smaller number of points, few points, not only 1 point, but few points. But so in that case, I can call it removable discontinuity. But otherwise, in a function, if I have to change the whole characteristics of the function, then obviously it will not be removable. So this removable discontinuity again generates an entire class of problems where you will be asked the question at how I can remove the discontinuity, in which case you will simply put it that set f0 equal to 1, and this will remove the discontinuity that we observe in this function. Okay. Okay, so now we will look at three theorems. One of them is quite composite. I mean, many statements are written together. So one of them is kind of the continuous counterpart of the basic limit theorems. And the other one is something that is really helpful in a subject like economics. And then there is a third one. Okay. So number one. So this is a theorem. So let's write theorem 1. So let f and g be continuous at point P. Okay. Then the sum f plus g, comma, the difference f minus g, comma, the product f dot g are also continuous at P. Are also continuous at P. Okay. For quotient, you can understand, you have to define a little extra. So the same is true. The same is true of the quotient f by g if g of p not equal to 0. Okay. The second one, no, which is not really a theorem, rather. The second that I'll write is a result, and this result is pretty important. Every polynomial px so px equals to, so we'll write a polynomial in the smallest possible abbreviation, sum over k runs from 0 to n, c with a suffix k, and x to the power k. So this is continuous. This is basically the functional definition, structure of a polynomial. So it's continuous at all points. Now this result is pretty trivial, but why this result is important? Because we have to work with polynomials a lot of times. Polynomials will play a very, very important role in our work. Okay. Now the last theorem, and this is interesting actually. Theorem 2 continuity. Its name is continuity of indefinite integrals. Continuity of indefinite integrals. So what does it say? Assume f is integrable. Assume f is integrable on closed a comma x for every x in close a comma b, and let a of x is equal to integration a to x f of ft dt. Now, I'm writing this statement, but before that, just to say, see, this is an indefinite integral. You have seen it all the time. The one thing that you have to note first here is that before even completing the statement, that this integration, this integrand, rather integral, if I write it as a function, which it always is, it becomes a function of x, right? This x. Remember that. Okay, so this is done here. Then the indefinite integral, a is continuous, then the indefinite integral a is continuous at each point of close a comma b. Okay. And here we'll have the application of one-sided continuity. So at each endpoint, that is at point A and point B, we have one-sided continuity. One-sided continuity.